Okay, so what did we do last time? Last time we did a bunch of optimization review stuff again. Say like part 2. And we mostly focused on constraints, right? We talked about equality and inequality constraints, Lagrange multipliers, KKT conditions, and sort of some algorithms for solving inequality constraint problems at a very high level, right? Okay, and today we're going to get into one of the sort of like bread and butter topics of classical analytical mechanics, optimal control, et cetera, which is calculus of variations. And I'm going to give you a very sort of non-standard Zach version of this that hopefully makes some sense. I think it makes more sense, at least to me, than the like standard ways of talking about this stuff. Has anyone seen this stuff before? A little bit. Where have you seen it before? And you talked about the stuff in RoboMath? Okay, interesting. I didn't know they covered this. That's good for them. Cool. All right. So for those who have seen this, what would you say? What is this about? Like, what is this whole thing? So yeah, what it's really about is it's calculus on functions instead of vectors or scalars, basically. That's the gist of it, right? It's basically how you differentiate a function with respect to another function. So we're going to talk about like what that means. And the fancy name for this, by the way, is Frichet derivative. There's like all these generalized notions of derivative with French dudes' names attached to them. There's like Gateau derivative. Anyway, there's a lot of those. So this is kind of one of those, but it's much, much older than those fancy French guys. This dates back to Newton, actually. Like Newton came up with these ideas to some degree. And okay, so last time we looked at kind of your standard flavor of optimization problem, something like this, where F is from like Rn to R, right? So X is a vector, right? It eats a vector. And F, our objective function, is a mapping from Rn to a scalar. So we're going to call this, in this context, this is going to be called a finite dimensional optimization problem. And by finite dimensional, we mean specifically that X is just a standard vector. It's n-dimensional, right, in Rn. Cool. Okay, so in like lots of areas of dynamics, physics, optimal control, shows up in a whole bunch of areas. We often want to solve what are sort of called infinite dimensional optimization problems. And I'll explain exactly like where this comes from. This sounds super weird. It's not that crazy. Okay, so here's the way we're going to think about this, like infinite dimensional idea. So we have this X up here, right? That's our decision variable for our optimization problem. Let's imagine that X is a vector of samples actually, sure this is recording. Okay. From some continuous function y of t. And what I mean by that is like, think of this as a trajectory. And yeah, like in this context, obviously trajectory in optimal control, obviously also trajectories, right? That kind of stuff. So we've got, you know, some t, got some wiggly thing, say, whatever. This is y of t. And let's say we take a bunch of samples at discrete time steps, right? So we've got t1, t2, dot, 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 all the way over here to like tn. And x is going to be all these samples. So it's going to be like y1, y2, dot, dot, dot to yn, right? Sampled at some like time step or some sample rate, right? Okay, so the idea is if we increase the sample rate and the dimension of x increases, obviously, right? And the vector gets bigger. The dimension of the vector gets bigger. Okay, so the idea behind this whole like infinite dimensional optimization thing is just what we're going to kind of think about as it's the limit as we take the sample rate to infinity, or like the step size to 0 of this thing, in which case what we get back is the actual continuous function y of t, right? So the way to think about it is functions of a scalar, i.e. trajectories, where you've got like a y of t, that thing is considered an infinite dimensional vector. Does that make sense, everybody? That's cool. Okay, so trajectories, basically when we say trajectory, what we really mean is a function of some scalar, right? Like r to rn. And so that can be time. It could also be other things. You can think of these. Think of these infinite dimensional vectors. So any questions about this idea? This is like a little fuzzy, but hopefully it kind of makes sense. Okay. Another way to think about this, right, is like you're going to replace your discrete in the limit, right? Your discrete index k becomes this continuous t, right? Cool. Okay. So now what we're going to do is, now that we got this notion of infinite dimensional vector, blah, 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 we're going to now talk about defining your cost or objective function such that it can eat these infinite dimensional vectors, right, and spit out a scalar. So what does that look like? Now, everyone's favorite cost function, x transpose x. That's pretty cool. Okay, so if we write this down in components, this is basically like following the kind of the stuff we had before. This would be like k equals 1 to n, 1 over n yk squared, right? Where we had those sampled y's, right? Cool with that? Okay, so the idea here is if I take the limit of this guy as n goes to infinity of this f of x, what do I get? Anyone have any thoughts on this? So we're going to call this capital F y of t for arbitrary reasons. Anyone have any thoughts on this? What does this thing turn into? Not 0. So the 1 over n out here in the limit, this is going to become like a dx, right? Or dt. Yeah. Like t equals 0 to 1, like y squared. Yes, you got it. Yeah, so basically this guy is going to become like your dt. right? And it turns into an integral. 0 to, yeah, we'll just go like that. That seems fine. Y of t squared dt. You got it. So basically, like these sort of inner product-y things on vectors, when you take this limit as the sort of number of elements in the vector goes to infinity, and the vector index becomes a continuous t, right? Basically, what's happening is this sum turns into an integral. Does that make sense to everybody? That's what it is, right? Okay, cool. So there's fancy names for a lot of this stuff. We're going to try to avoid as much of that nonsense as possible. I will tell you the fancy names in passing, but we don't care about them. These sort of things, people make a big deal about this. They call these sometimes functions of functions. So in this context, right, like y is a function, and this big F is a function of y, therefore it's a function of a function. And so people sometimes call this a functional. Anyone's heard of that? I would just call it a function. I don't think it's that big a deal. Okay, so now what we're going to do, the whole game here is we're going to take something like this. This is now what our F looks like. And we want to minimize F, say. So now what I'm trying to do is minimize, instead of F with respect to X, I'm trying to minimize this big F with respect to Y of T. And this is what F looks like. And we're going to do the usual things, i.e. take the gradient and set it to 0. But now I've got to take the gradient of this weird integral thing with respect to Y of T. So that's where we're going next. Okay, so we're going to sort of take this. First, we're going to look at the discrete version. So this is our normal, like min over x, f of x. And if we sort of do the same stuff, right? So this is what we had there. I can take, partial f, partial x in the usual way, and I'm going to get 2 over n x transpose. And then we set this whole thing to 0. And this tells us that x star sort of trivially has to equal 0. I maybe should have picked a more interesting function, but it's a bowl centered at the origin, blah, blah, blah. Okay, so now if we kind of write this down in components, this is like your standard vector notation that we all kind of know and whatever. If we look at this in components, we can start to get kind of closer to this like functional story. So the component-wise version is min over x, sum from k equals 1 to n, 1 over n, yk squared. And okay, so here's what we're going to think about this as. So this is like this whole thing, right, is your f of x, right? So f of x is a nonlinear function. This is where we start to get into this like weirdo generalized derivative stuff, this like Frechet derivative idea. So this is a nonlinear function from Rn to R. Its first derivative, one way of thinking about the derivative is that's the best linear approximation to f of x at the point x, right, that you evaluated at. And this also is related to my whole rant about gradients are row vectors, not column vectors. It's related to this idea also in the following way. So what the real deal here is that what the gradient of f really is it's another function that similarly eats a vector and spits out a vector the same dimensions as f. It's just a linear function, right? It's the linear function that best approximates f at a point x, right? So this is kind of my rant about f's being gradient, the gradients being rows, because what that thing is supposed to be is a function that eats another vector, spits out another a scalar, right? So that's got to be a row vector if it needs to eat a column vector, blah, blah, blah. Okay, so that idea of the gradient's really a linear function is what we need to kind of move forward. And so what we're going to try to do now is generalize that to that infinite dimensional case. So here's what that looks like, right? So if I've got like my f of x plus some delta x, I approximate this as f of x plus partial f partial x times delta x. What I'm gonna like really kind of think about this as, well, I guess I'll write it down. So for our particular example, right, I had like 1 over n x transpose x plus 2 over n x transpose delta x, right, for our specific example. So the way we want to think about this is this thing down here, this thing, which is the gradient, you know, times the new delta x, that whole thing, we're going to think about that as a linear operator or like a linear function. That we're going to sort of, we can write it this way, right? df dx of delta x, right? So it just so happens, right, like with linear algebra and stuff like this, when it's finite dimensional, I can write this as like a matrix or a row vector, whatever, times this guy. But in some generalized sense, what I want to think about this is just, this is a new function and it eats a delta x and spits out like a new x, right? So think of this just as some generic function now with an argument, right? It can look like this, or it can look weirder than that. The only requirement is that it's a linear function in that like abstract sense, right? That it obeys superposition and blah, blah, blah. Okay, so if we now take the limit of this thing, we're gonna, that's terrible. Wow, so bad. Hopefully you can read this stuff. At some point I want to LaTeX this stuff, but it's, yeah, I haven't gotten there yet. Also, when I make mistakes, definitely tell me. That's the other thing. Don't be shy. Okay, so here's what we get in that like infinite dimensional case. We've got now big F of y of t plus, maybe I'll start doing this. We'll do this because it's like historically, I'll throw it in at the end. I don't know. Okay, so we got some delta y of t. So this is our trajectory. This is some small perturbation on this trajectory, which is itself a trajectory, right? It's some function, trajectory, blah, blah, blah. Okay, so in the sort of like standard way, we're gonna sort of be very loose with the notation, and I'll kind of like hopefully fill it in later. This is what we're going for, right? Okay, so let's write this out. So we have this integral y of t squared dt. And now we're going to basically dip inside the integral. So we're allowed to do this because what we're doing, this is just an aside, right? So I'm going to dip this thing with respect to y. The integral is with respect to t, right? Which is a different variable. Therefore, I'm allowed to dip inside with respect to y, right? Everyone's cool with that? There's sort of this standard calc, like multivariable calc result about differentiating inside integrals and stuff. Okay, so if I do that, I'm going to get integral from 0 to 1, and it's like exactly what you expect. So like 2y of t, and then that thing has to get multiplied by the delta y of t. And this whole thing gets integrated dt, right? So this whole thing now, right? Because remember, like I've got to still like integrate this thing. This is kind of where it gets a little weird. This entire integral now as a function of delta y is the derivative, right? Does that make sense? So this whole thing is sort of df dy of delta y. Okay, so it's not as clean as like the matrix version, although if I discretize this in time and write out some quadrature rule for the integral, this does turn into a big row vector, right? As you would expect. So in discrete land, it is exactly the gradient you'd expect, but in continuous limit, it's this integral thing. And to evaluate the gradient, like really what this is the gradient vector product, right? Is what this whole function is doing. So if you like, Jacobian vector products from like, your TensorFlow or whatever, that's kind of the way to think about this. It's a thing that evaluates like gradient vector products, right? I can plug in a vector and I get the gradient vector product by taking this integral. Is that cool with everybody? It's like a way to think about this. Okay. So now what we got to worry about is we need to figure out now, like, in the classic, set the gradient equal to 0 optimization world, it's pretty clear what that looks like. Here, it's a little more subtle what setting the gradient equal to 0 is, right? So the idea is at a min, f of y is locally flat. And there's the same kind of notion as before, right? So doesn't change for small, I'm using like specific language here that's like, so we're going to use this word variations, delta y of t of the function y of t. Okay, so the idea here is, if I sort of write that in math now, this function of delta y, which we figured out, this thing has to equal 0 for all delta y of t that I plug into it. That's what this means, right? And the only way that works is if this guy that multiplies it is 0 everywhere. Does that make sense? Okay, so that's how it works in this context. Okay, so that's where we get back to like the thing we sort of, all these arguments are the same in the vector case, right? They're just a little more subtle here. Like all this carries over, it's all the same stuff. It's just like a little weirder looking, and you got to think maybe a little bit more carefully about it. Okay, so the last thing I will mention is we use kind of like vector standard, more like vector calculus notation here. The standard notation in calculus of variations for this stuff, one is that you call this little delta y of t guy, this like what would be like a differential, right, in like regular calculus, like as a vector. This is called a variation, and that's like a delta function. And they use a specific notation for this that I did not use, but it's sort of the same ideas. So they call these things, they use little delta for these like variations on functions, and they write it this way. So you would write little delta f, i.e. variation in the objective function, is equal to this thingy. And you write the delta on the y in there too. And so this is called variation of y. And this is called variation of f. And the main thing is they write it this way. They never write really like df over dy like we normally do. And it's kind of because in this context, you've got to think about this thing as this like linear operator function-y thing that has to eat a delta y. So you can't really like divide through by delta y here in the same way we normally do, right? So they kind of always write it like this. Okay, any questions about this? It's like a very quick and dirty tour of calculus of variations.
Why is not
Why? Yeah, so in this particular problem, which is a trivial problem, and it's analogous to the bowl, quadratic bowl centered on the origin, right? Like x star has to be 0 in the continuous example. All I did here was like I blew up the dimensions, right? So like x transpose x in 2D 10D, 5,000 dimensions, right? The answer is the same. The vector x star just gets bigger, but it's still zeros. This is just like the very, very big dimensional limit of that, where I have lots of dimensions, but the function's the same. The zeros still the minimum, right, of that big bowl. It's just in like a very, very high dimension, infinite dimensions. And like it's a function now. And the way to think about it, right, it's like your index k for your vector just becomes this continuous variable t now. So this is a function y of t that's got to be identically 0 to satisfy this optimality condition, right, that I got here. It was a very simple example. But yeah, does that kind of jive? Make sense? So this is the notation you'll see like commonly, like this little delta. And like the way to think about it, right, it's like having a dy in regular calculus. They just write it with that little delta to be fancy, and right, it's a function. Okay, cool. All good? So now we're going to start looking at a more interesting problem that we'll spend some quality time with. That is the one that is on the homework. And we're going to, for me, this is like basically the simplest problem that has all of the flavor of like all of these calculus of variations problems, and like captures like kind of the real heart of what's going on. So I'm a big fan of this one. And it's also like somehow super general, like the same ideas apply for basically like every other calculus of variations problem. So, and I think it's fairly intuitive compared to some of the others. So what we're going to look at is this hanging cable or hanging chain problem. It's called the catenary problem. It's one of the like old classical problems. I think this was solved by the Bernoullis maybe in one of these old things. Okay, so this is the cable. We're gonna have so let's see, let's make some notes. So we've got gravity, and this is a support, and we've got our standard sort of XY coordinates in the plane, and we're going to discretize this guy along the x-axis. So you've got, you know, x1, x2, dot, and then over here is going to be xn, and this is x naught. And so x, the x coordinate here, is going to play the role of time in our, so we're going to treat this as a trajectory in x, right? So we're going to solve for y of x. It looks exactly the same as y of t, right? Just as x is one dimensional and all that stuff still checks out. And let's see, what else is there to say about this? This is our cable. We have known fixed endpoints. So we know y naught and yn at x naught and xn. What else is there to say about this? We've got, so the whole width of this is w. So i.e. like w equals xn minus x naught, right? And then we're going to draw now a little picture that hopefully I don't completely butcher. So we're going to take like one of these little segments and zoom in on it, and it's going to have sort of a delta x k and a delta y k. And the length of this guy here, we're going to call delta sk. All right, so let's write this out. So this delta sk squared equals delta xk squared plus delta yk squared, right? So if I zoom in real close, infinitesimally, we're going to say it's a little straight line segment, blah, 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 triangle. So this is an incremental cable length. And what else is there to say? And then like the delta x is a fixed number because we have a fixed discretization here that we just like plop on there as part of the setup. This is equal to just w over n. Got n steps. Cool. Actually, it's n minus 1, isn't it? N minus 1. Okay, cool. So now we need some stuff. So first thing, we're going to write down the total cable length, which is not W, right? So we're going to call this L. This is sum over all the delta S's. So K equals 1 to N minus 1, I guess, delta SK, which is equal to, sum K equals 1 to N minus 1 of square root delta XK squared plus delta YK squared. And then remember that delta X is a constant. So I'm going to pull the delta X out. So we're going to get delta X times 1 plus delta YK over delta X squared. For reasons that will become clear later. This is a convenient thing to do. Just pull this out. Okay, all good on that? Literally just summing up all the little triangle guys, right? Okay, the next thing we need is the total mass of the cable. So like we know what this is, it's a given, but it's going to be some M, and it's going to be the sum over rho, which is some density, times these delta S's, where rho is defined to be sort of total mass over L. This is like the incremental mass of each little chunk, right? Okay. Now we ask the question, what is the shape of the cable? That is the problem. So let's think about this for a sec. So as like a dynamics problem, I could write down the dynamics of this floppy cable. I could approximate this thing as like a whole bunch of little springs and masses or something, right? And I could get down x dot equals f of x, like a dynamics function. And then I could solve that dynamics function for an equilibrium, x dot equals 0, right? And there should be a stable equilibrium where it's hanging down. And I could find it that way, right? So that would be cool. Another way to go is, if I think about this a little carefully too, at rest in this hanging configuration, it's not moving at all. So it has 0 kinetic energy. So another way to find this is it's the minimum of the potential energy. So if I wrote down the potential energy and I just straight up minimize it, I find the lowest potential energy possible configuration, it can't move from there, right? Like if I had a little bit more potential energy, under gravity, it's going to fall and it's going to gain some kinetic energy and move around. But another way of finding this is just straight up write down the potential energy for the whole thing and minimize it and find the shape that has minimum potential energy. Is that clear to everybody? Okay. Okay. And we're gonna, like I kind of just said, we're gonna think of the cable shape as a trajectory. So y of x, right? Where x plays the role of time. Okay, so far so good. Questions? All right. So what we're going to do next is we're going to kind of keep playing in discrete land. So we're going to discretize. I mean, we kind of already have this discretized picture. So we're going to keep it with the discretized picture and kind of do this in discrete land. Then we're going to take a limit and show you the continuous version of this. So let's discretize. So we're going to write down the potential energy. That's the main thing. So we call this U, and it's sum from k equals 1 to n minus 1. So it's just mg, right? It's mg for each little chunk, right? Okay, so the m is up here. M for one little chunk is rho times delta S for that chunk. And then it's G times the height, right? It's MGH. So here's M. Then we've got G. Then we've got to write down the height. And what I'm going to use for the height is a midpoint approximation. So I'm going to take like the average between YK and YK plus 1, right? And that's my like midpoint height for that little segment. Okay, cool. So now I'm going to just plug in the stuff from up here where we defined like delta SK and all this other crap. Yeah, and I should write. This is MK. Okay, so this guy's sum from k equals 1 to n minus 1 of rho G. Got the height thing. And then we've got this delta S, which I'm going to write kind of the way we had before. Right this way. Okay, cool. So that's just me plugging in all the stuff from before, right? Okay, so now we're going to define the optimization problem we're actually going to solve. So we're basically going to minimize this thing, like we said, but there is a constraint. Okay, so we've got min over y 1 to n minus 1. This guy, k equals 1 to n minus 1 of rho G midpoint height. And then the length thing times delta x. Cool. Subject to, so what constraint would I have in here? Does anyone have any thoughts on this? Like, why do I have a constraint? Where's that show up? Yeah. You got it. Yeah. So basically what I'm doing, right, is I've got all these little, I'm like letting the y's be whatever, right? And that affects the overall length. So I've got to actually set up a constraint such that sort of the sum of all these delta s's adds up to L, the total length, right? So we could write that like so. So we've got sum over delta sk. So that's k equals 1 to n minus 1 of this guy. This thing minus L has to equal 0, right? That makes sense to everybody? And yeah, the one note I specifically in here, right, this goes from 1 to n minus 1. The n, because I'm assuming the endpoints are given. So why not and why n are known. Okay, so let's dig in. So the main note here is this problem has a lot of structure. It's not like a generic optimization problem. And this is going to be some like a big thing. We're going to make a lot of sort of a big deal about this. And this is kind of the entry point. Okay, so here's what we're going to do. This is messy and ugly, and I don't want to keep writing all this crap. So what I'm going to do is like, we're going to like sort of just simplify this down to a very generic form of this problem, and then we can plug the specific details back in later. So here's our generic version. You do like min over x, sum k equals 1 to n minus 1 of f of xk plus 1, subject to sum k equals 1 to n minus 1, c of xk equals 0. So this is exactly what I have up there. I'm calling this whole big messy thing f, and this whole thing c, right? All good? Okay, so what I'm going to do now is I'm going to put this all together, and I'm going to write it down. I'm going to write the Lagrangian for this problem, Lagrangian in the optimization sense. So I've got L of x and lambda. I guess these should be y's. Huh? This is annoying. Okay, so we got sum n minus 1, f of yk plus 1, plus we're going to get our Lagrange multiplier lambda, and then we're going to get our c of yk. Okay, you cool with that? And in particular, I want to just point out, this is a single Lagrange multiplier, 1 lambda, right? Because that's a single constraint. It's a 1D constraint, just this one length constraint. So there's only one multiplier. But then this C thing is defined sort of component-wise as a sum, right? Okay. So now what we're going to do is write down KKT conditions for this thing. So I'm going to just take partial L, partial X. We're going to write it kind of the way we were before. So if I'm now, what I'm going to just do is go dip inside the sum, right? That's legal. So I'm going to introduce some slightly weird notation. I think it makes more sense in this context. So this is called a slot derivative. It just means take the derivative with respect to the first argument of this function. So that's the first one. So I got to differ with respect to the full x vector, which is with respect to all the yks, all the y components. So that's the first one here. I've also got to differ with respect to the second one. So then I'm going to get a d2 f yk plus 1 times delta yk plus 1. Then I'm going to get the Lagrange multiplier term. So I got lambda d c of x k delta x k. And this whole thing has to equal 0 for all delta x. Oh, I messed, this is a y. Okay, so this thing's slot derivative. Just derivative with respect to whatever index. And then the other one we get is partial L, partial lambda, just gives us the constraint. Okay, cool. All so far so good, super straightforward. Okay, so now there's a little bit of a trick. So this is kind of annoying. So this thing, I define this thing with this sum. Remember, like at the endpoints, we've got terms that involve yn and stuff in here, and we know those are fixed. And I ultimately want to get some like first order necessary condition thing for this that's clean. And specifically what I'm after is I want to get some expression where I can pull out just a delta yk, single index yk to the right, and like write down these clean first order necessary conditions, like this clean partial L of x as a clean sum. So that's what we're going to do. To do that, we're going to play an indexing trick. And like really all we're going to do is we're going to pull out the first term and the last term from the sum and realize where the y naught yn terms are and kind of get rid of those and then rework the middle part of the sum. So I'm going to pull out the first term, which is going to look like x1, x2. I guess I'm sort of messing up. This needs to go from k equals 0. Not this one. These should be zeros. Okay. So this one's x naught x1 times delta x naught. Then we've got d2 then we've got the Lagrange multiplier term. And then we've got the sum in the middle that's now going to be indexed from k equals 1 to n minus 2. So I've knocked off the first and last terms. That looks like this.
Hey, Zach.
Yep.
Why did we switch from y's to x's here?
Oh, because I'm just being terrible. I'm trying to keep it all straight and I keep screwing it up. So I was using x for the whole vector with all the samples, and I was using y for the samples. Sorry. Okay. I'll try to. This is why it's bad to go off script. It's tricky to keep all this stuff straight. Okay, so what did I have? yk plus 1, delta yk, yk plus 1, delta yk plus 1, and then Lagrange multiplier thing. And then the last term, which I'm also going to pull out. So here we got which one? Oh yeah, sorry. This is layers of notation that I'm trying to parse on the fly that it's not going well, obviously. Okay, sorry. Here we go. So we got the last term now, f at xn minus 1, y. Yep, it's already off the rails again. Yn minus 1, yn, delta yn minus 1, plus d2f, we got n minus 1, n, delta yn, plus the last Lagrange multiplier term. Yn minus 1, delta yn minus 1. Okay, that's the whole thing. I just pulled the first term out and the last term out from the sum. And then I say, hey, I have fixed endpoints. So delta y naught and delta yn have to be 0. So then I go in here and I get rid of those terms. So this guy goes away. This guy goes away. And this guy with the yn goes away. Cool. So now what I'm going to do, now that I just pulled those out, I'm going to suck everything back into the sum and just like rework the indexing. So I can suck these terms back in. And because I like zeroed out those other ones, I can write this whole thing now as sum from k equals 1 to n minus 1, d2f yk minus 1, yk, delta yk plus d1 Okay. Is it clear how I did that? I basically like took this guy and called this yk minus 1 yk delta yk. Stuffed it in here, right? So I just reworked the indexing. Note the indexing here is the same as here, right? So I started at one index later and stopped at one index early. Is that clear? I just like sort of played a little index trick. Okay, so that's cool. And the reason we did this is so now everything's at the same time step in here. So I can factor out the delta yks and I got my like thing that I wanted. So I've got this function that I was after. This is 1 to n minus 1. So I'm going to put this whole thing in brackets. So this is d2 1 and then the constraint term. Okay, lambda, cool. This whole thing times delta yk equals 0. And this has to be true, just like before, for all delta yk. Okay, so the punchline is, just like before, for this to hold for all delta y's, the thing in the brackets has to be 0, right? For the gradient thing to equal 0. It's exactly the same as the stupid example we did first. Oh, that's terrible. Okay, that's the punchline. Okay, so this is actually worth thinking about for a second. So we started out with this like big optimization problem over the whole cable. So there's this giant sum, and I was minimizing this whole trajectory, right? This like big X whole vector. What I have here now is a like local optimality condition that only cares about yk, and it's like immediate neighbors. So like yk minus 1, yk plus 1, and like this thing. So this is like zoomed in at one of those little segments. And this is saying for that little segment, for the whole thing to be optimal, I can actually just look at these little chunks individually over the trajectory. This should be ringing some bells if you've ever done any like, optimal control or whatever. So these are local. They only depend on like immediate neighbors. And we can use this to calculate the whole trajectory just given some initial conditions or given boundary conditions or whatever, right? Uh, More to come on this. Does this sound familiar to anybody? It's like a local optimality idea of like, does this look like anything you've seen before? It's, yeah, it's another instance of that. There's something like kind of, there's a deeper thing. We'll get there. Okay, cool. So that's the whole thing. When does this end? Is it 11:30? Okay, I always like get this confused. Okay, so now what I'm going to do is just like do this in the continuous limit. So we're going to take this limit as n goes to infinity, and sums are turning into integrals, all the usual stuff. So this is now min y of t integral from 0 to t. Oh, yeah, this is like, should I do this as, yeah, we'll do it like this with t's. That's fine. I don't know. There's like notational quirks here that I'm trying to. So y of t. So the important thing that happens here, if we kind of go back and look at this, right? I've got stuff in this guy. I'm gonna go all the way back to the top just for a second to highlight something. Okay, so I've got this like delta y over delta x thing in here, right? And what I'm doing when I take the limit as n goes to infinity, I'm taking also the limit as delta x goes to 0, right? And we argued this is going to turn into like your dx and your integral. What's this guy going to turn into? About like a delta y over a delta x in the limit. Yeah, it's going to turn into like y dot, basically. That's going to turn into like a velocity squared in this case. Okay, so that's the important message. So like in the discrete version, I have like yk plus 1, because that's what that thing depends on. In the continuous limit, that's going to turn into like y and y dot. Does that make sense to everybody? So the continuous version of this looks like so. And then we've got the constraint here, which is going to be basically this, like the integral version of that like thing that we had before, which I'll just like simplify as, oh, maybe we should do it like, so we had like integral from 0 to t of, what was this, like s of y dot, basically dt equals L. Okay, cool. We're gonna do the same stuff. So we got Lagrangian in the optimization sense, y of t lambda. So we're gonna kind of pull everything in. So we got f of y dot. I guess I'll put the t's on there for emphasis. Plus lambda times our c, or I guess this would be, yeah, we'll call this c. I'm sorry about the notational quirks. I'm like, to be consistent, I will call this c of y dot. That was our generic version, and equals 0 to keep everything straight. Okay, so we got lambda, we got our c. Everything's integrated dt. Cool. And then we've also got, okay, so that's the Lagrangian. I just stuffed everything together just like in the sum version. Now we're going to do KKT conditions, just like before. And here, I guess I should put these in quotes, since they're KKT conditions as far as we care. They have fancier names, blah, blah, blah. We'll talk about that in a minute, but we'll kind of stick with our fast and loose versions of these things. So we're taking dl dy of t, and it's this function that's going to eat a delta y of t. Okay, so I'm just going to diff inside the integral like before. So I get d1 f y of t y dot of t times a delta y of t. And I'm going to get a similar, I get d2 f y y dot times a delta y dot of t. And then I'm going to get a Lagrange multiplier term, lambda I'm going to make this a little simpler. Okay. So far, so good. And then, like, obviously, if I take the lambda derivative, I get back the original constraint. Okay. Cool. So what we're going to do next is like kind of the key move in like all of calculus of variations that like I feel like it's sort of maybe poorly motivated, but this is what you do. So the idea again is I want to get this thing to look like stuff times delta y of t inside the integral, right? And then basically I want to factor out delta y of t and then argue that all the stuff multiplying it has to be zero for this like gradient equals zero condition to hold, right? This actually I needed to do equals zero. Okay, so in order to do that, we're going to play a trick. Basically, right now, it mostly looks good. The only issue is there's always delta y dots floating around. And I don't want the delta y dots. I want to make everything delta y's so I can like factor out the trajectory. This is very similar to the discrete case where I wanted all the indices to line up, right? Like it's the same idea. And the goal is like these local optimality conditions. But the delta y dots mess us up. So we want to get rid of the delta y dots. Here's the key trick. You guys know what the trick is. What's the trick? You did this before. If you've done calculus variations, what's the move? Is this like key move that like I feel like is okay? So the trick is integration by parts, which is from like high school calculus, but I never remember it. But it's actually easy. This is one of those things where I don't know how the original person came up with this, but you know, now we know. So where this comes from, it's just like the inverse of the product rule, right? So if I have like two functions, u and v of t, and I do this, right? If I expand that derivative out, I get u dot v plus u v dot, right? Okay, so that, and so if the integration parsing is just inverting this, so I get u of t, v of t, integrated, sort of, so evaluated at the endpoints equals integral u dot v dt plus integral u v dot dt. So I'm just like integrating everything, right? Integrate both sides. Now I can like just move this around and write it as integral of u v dot dt equals u v evaluate the endpoints minus integral u dot v dt. So there's like a little heuristic here. So like, okay, so the reason we're doing this, to be clear, is I have some stuff up there where I've got y dots or delta y dots. I want to get rid of the delta y dots. I want to get rid of the dot on the delta y dot. So this thing lets me, so if I have this one, right? Like think about this as my delta y dot and this is whatever it's multiplying. What I want to do is flip the dot. This lets me flip the dot and pick up a boundary term at the endpoints. What do I know about the endpoints in my problem? They're fixed. So the endpoints, there's zero variation. The endpoints, so I can get rid of this endpoint term. This is exactly the continuous version of the index trick that we played in discrete time, where I pulled the endpoints out. I pull the endpoints out, argue that these things can't change, so this is zero, and I get to flip the dot and get rid of the y dot term that I don't like. That's why you do it. I feel like this is, I have never found a good, like, intuitive, like, version of this story, but this is the trick that, like, make this all work in continuous time. In discrete time, I feel like I could have figured that out. It's, like, fairly, okay, yeah, I could see that. I kind of feel like whoever originally came up with this, like, had to have done it in discrete time and then, like, taken a limit and realized, oh, wait, this looks like integration by parts. Something is super weird to me. Anyway, that's what it is. In discrete time, I feel like it makes sense. Here, it doesn't. But this is what they throw at you in, like, any sort of standard course on this stuff. So I don't know. I gave you the Zach version in discrete time, which hopefully makes some more sense. So you get this boundary term, and you get to flip the dot. Okay, so if you apply this now to our KKT conditions that we had before, get some more space. So we've got this thing. I've got my integral. I'm going to be a little loose and stop writing the of t's on all these guys for a minute. So, okay, so I'm going to do this to the delta y dot term. So what's going to happen, right? I'm going to get to take the dot off the delta y, and now I have to take ddt of the first term. So that's where this is coming on, and there's a minus sign on here. Whatever. Okay, so I'm just going to plug that in over here. So minus ddt of that first term, which looks like this. And now it's delta y instead of delta y dot. And I guess I have to do that to the other stuff too. So the C term as well. And minus C. Okay, so that's cool. And then we pick up the boundary term. This is the integral. I need to write dt on here somewhere. Okay, dt. Now we get the boundary term, and you already know what the punchline is there. You're going to get a thing that looks like the original stuff. So d2f times y at t equals 0. I guess I'll write this all out. Right. Okay. And then this is basically this whole thing evaluated t equals 0 and t equals big T at the endpoints. And since we have fixed endpoints, this has to be 0, blah, blah, blah. This whole thing goes to 0 because of the fixed endpoint thing. Okay, now you can pull out the delta y completely over here, like so. And you get d1 f of y dot minus d dt 2 f dot, and then we're going to pick up like the lambda terms. Okay, that whole thing has to equal 0. I will now write this in a, I'm going to get rid of the slot derivative stuff. The reason I did the slot derivatives, by the way, is to keep track of the indices. It's like a lot easier than having to like partial with respect to like whatever sub k is, and that gets hard to read. So I'm going to rewrite this with like normal partial derivative notation real quick. So this is going to look like partial f partial y minus d partial y dot plus lambda times partial c partial y minus d dt partial c partial y dot, all equals 0. Okay, what does this thing look like? That part at least, right? This is the Euler-Lagrange equation that you've probably seen before. Okay, so in the same spirit as like the stuff we did before, this is a second order ODE for y of t, right? So given initial conditions like y dot at t0, we can integrate this thing continuous time and get the shape of the cable or whatever. And we're out of time. Okay, that's the story. So we're going to do some more of this next time. So I guess Tuesday, where we'll take another look. So I did this basically two ways. I did it the discrete way because I feel like that's more intuitive. The continuous version with this like integration by parts trick is the standard move. You can take this discrete time version up here. I showed you that just because you should know about it because that's the way everyone else does it. The way I would actually do this if it were me is I would take this discrete one that we derived and just take a limit of this guy directly. You take this and just straight up take a limit of it, you'll get the Euler-Lagrange equation. So in some sense, this guy up here with the indices, this is a discrete time Euler-Lagrange equation, right? And you can get them without doing the integration by parts nonsense by just taking the limit as n goes to infinity of that sum guy and getting the integral back at that level. That's it for today. There's a lot of math. Hopefully I didn't like completely lose you. Next time we'll take next time we're going to zoom back in on the hanging chain problem and like actually do the hanging chain with this math both ways, continuous discrete, and like talk a little about it. Hopefully show you a little more like insightful nuggets about like where this comes from. I wanted to give you like the classic version, which is this at least, so you know about it. But I think there's like another, I think if you've got a CS flavored background and you've seen like some optimal control, some RL, some dynamic programming before, I think there's a much more intuitive way of looking at this, which we're going to do next time. So just to keep you, burning for more. That's it for today. Thanks, guys. Thanks for